lecture. And okay, share the screen. Let's start from here. Yeah, let's wait for 1 minute. I think we are missing some students here, so it's 1 minute early. So, so any questions so far? So do you have any questions based on Tuesday's lecture? Good, very good. So, so do you have chance to try the R code I posted on the iLearn? So the chi-square distribution. So I provided some R code you can use to calculate different things for chi-square distribution, like the probability density function and a cumulative distribution, and find the quantile, something like that. So I'm gonna demonstrate today using those code. Okay. All right, let's get started. Okay, let me stop sharing first. And let me show where's my R? Okay, here. All right, so you can see my screen, right? Okay, so this is the code, R code I provided that you can try, and they are very useful because in the final exam, you may use some of this to help with your calculation. If I ask you to do something like the power analysis, the sample size analysis. All right, so this is very basic functions that you can use in R. So for example, so you do not have to include any package for implementing this R code, because those are the basic R functions. So it has been they have been already included in the R package, basic package. So this is the function called the d chi-square. So the chi-square is for the distribution type, and the d means the density function. All right. So if you use d norm, so of course that is. Can you see my screen now? No.
Yes.
I mean the website. Can you see this? The normal distribution?
No, now we can see your R code.
Oh, just R code. Okay. So let me stop this. Okay. So if you you see my R code just now, right? So if you type a question mark and d norm, so it will, the website will be popped out. Let me see. Where's my web page? This, okay. So this information will be popped out. So it's the information about the normal distribution, and here d norm is the function that you can use to calculate the density for the normal distribution. So okay, let's go back to our R code. So here, okay, so we use density function to calculate chi-square, right? All right, I'm gonna talk about what the density means for a distribution. So let's look at this code here. So this code is to calculate the p-value, right? The p-value. All right. So for the chi-square distribution, if you have a chi-square statistic here, and if you let the R know what the degree of freedom is, for example, here, the degree of freedom equals to 1. And if this is a central chi-square distribution, so the non-centrality parameter should be equal to 0. And all right, so this is another thing you need to tell R. So whether you're going to calculate the p-value for the lower tail or the upper tail. So I'm going to show you what that means. So basically, we calculate the area under the curve, right? Either left side or the right hand side. So these are corresponding to either the lower or upper tail. Okay, so this is okay. So this is usually like other options. So usually we do not change anything for this part. Okay, so this is the p-value calculation for chi-square distribution for central chi-square or for the non-central chi-square, right? So, but for non-central chi-square, you have to specify this parameter, non-centrality parameter. Okay, now the Q function means the quantile function. So you can based on uh, the p-value, the degree of freedom, and also the non-centrality parameter. So you can calculate the chi-square statistic, the value for that area, right? So this is one thing we can do. And okay, so these two lines actually so these two lines are not very relevant to our current content, but maybe in the future it will be useful for you to in your future research if you want to generate some random variable which are chi-square distributed. So R means the random variable generator. So you're going to generate how many this kind of random variable, and based on the chi-square distribution with degree of freedom equals to 1, and whether this is a central or non-central chi-square distribution. Okay, the last part. So let me show you. Okay. So we have talked about this, right? So last time we talked about the relationship between, oops, no. Okay, so we talk about the relationship between the Wald test and the z-test. So Wald test is a chi-square test, and the z-test is a normal distribution. So and this is how we can. So this is the relation. This graph shows the relationship between the z and the normal distribution and the chi-square distribution, and how we can use normal distribution to calculate this thing. This is uh, the non-centrality parameter, right? So basically, so this is what we can. This is the formula that we can use to calculate the non-centrality parameter. So we need to calculate the critical value for the normal distribution, which specify the area equals to R 1 minus alpha divided by 2, and also another one, right? So this is what I showed in this code. Oops, let me see. Okay, no worry. Don't worry. Yeah. Okay. Where's my R code? Okay, here. All right, so here, see, we just use the norm, the quantile function for normal distribution. We can calculate the z1. So you still remember the formula I just showed you, right? So how we can calculate the non-centrality parameter for the chi-square distribution. So actually we can use the normal distribution. We first calculate the z1 which is the quantile when the area equals to 1 minus 0.05 divided by 2. And this is a standard normal distribution 0, and the standard deviation equals to 1. And then we're going to calculate the lower tail. So I'm going to talk about what lower tail means, okay? So this is for the first calculation. And for the second, the z, we can still use the normal quantile function. But here, this is the 1 minus beta, right? So the beta here type 2 error equals to 0.1, and we need the power to be 90%. So that's 1 minus 0.1, and still standard normal distribution mean equals to 0, and standard deviation equals to 1. We also calculate the lower tail. And once you get the Z1 and Z2, so you just use the sum of Z1 and Z2 to the power of 2. So then you can calculate this non-centrality parameter equals to 10.5. So which is very close. Let me show you, which is very close to the example I showed in the class. Okay, so if you look at the example here, right? So it's 10.550. So it's very close to this one. So when you have time over the weekend, so please try this code and try to do this calculation to see if you can recover this calculation, these numbers. If you do, yeah, that's a good sign. So that means like you will feel very comfortable to work on my question on the final exam. So, all right. So now let's see what is the density function and what does the lower tail or upper tail means. Okay, here. Okay. Okay, so first, I hope you still remember, right? Here we have a non-distribution, right? Which is a central chi-square. The first one, the solid line, and the dashed line represented the alternative distribution, which is a non-central chi-square distribution, right? So these two curves actually are called the density function. So what does that mean? That's equivalent to the probability so this is actually the probability function for the continuous variable. This is a continuous variable. So the density means the density function y when your chi-square statistics take a specific value. So for example, if you want to calculate the density for the chi-square statistic equals to 10. So what is the density for the chi-square statistic equal to 10 when the non-distribution is true? So you go up and hit this curve. So this point, the y value, is the density for this chi-square statistic when the non-hypothesis is true. Okay, now if I ask you, what is the density for chi-square statistic equals to 10 when the alternative hypothesis is true? So you need to go beyond and hit this curve, right? That y gives you the density for, oops, y star equals to f star. So this is the alternative. So I put a star here. Okay, so the density actually is equivalent to the probability. However, this is a single point. So we sometimes are very interested in the cumulative distribution. So for example, let me erase this. So I hope you still remember. So in this kind of density distribution, so we sometimes are very interested in the area under the curve, right? So okay, so look at the solid line. So if the null hypothesis is true, so if we have a cutoff here. So we usually calculate the area under the curve, right? So this is something we are interested. So, okay, so if we calculate the area on one side, for example, the right-hand side, this is the upper side. We call this upper side because the numbers are larger, right? And if we talk about the area on the left-hand side, that's the lower tail. So because those numbers are smaller, right? So this is how we define the lower tail and the upper tail. Okay. And so when you use the code I provided to calculate the p-value for the chi-square distribution, so by default, if you do not change anything, by default it will calculate. I think it by default it will calculate the area for the lower tail, right? Until you specify the lower tail lower tail calculation is false, so it will calculate 1 minus this thing, gives you the area on the other hand side, right? On the other side. Is that clear? Okay.
I didn't quite understand your word usage there. I just misheard your words there. To calculate the lower tail, obviously that's already plugged in, and you specify lower tail. But for the other rest of the code, to specify the rest of the area under the curve, what do you do? 1 minus?
Yes, because the total area under the curve is equals to 1. So
Yes.
no matter what kind of distribution, so yeah, that's a good question. Let me say that. So okay, so oops. So if you look at the solid curve, so the area under the solid curve should be 1. So if you look at the dashed curve, the area under the dashed curve is also equal to 1. So that's the whole sample space. The total probability is always equals to 1, right? And so let's go back to the R code. Okay, so for example, so if you want to calculate, so let's see if you do not specify the tail, what does that mean? What will be that? So if you just let the R know, okay, the area we want to add that to calculate the, oh no, this is not the right one, sorry. We need to use this one, yes. Okay, so suppose you want to calculate the area, the probability of the chi-square distribution when the chi-square statistic equals to 3.884, right? And the degree of freedom equals to 1. And this is a central, so what does that? That means like the area on the left-hand side.
Okay, the calculation for that, it said lower tail equals false. So why wouldn't it calculate the entire area? I need to see the equation, which is being blocked by the window. Sorry.
Block the window? Okay, sure.
Yeah, there we go. Q squared 0.05, 1 NCP equals 0 means non-central. It's lower tails false. What log P, what does that mean? What's the value?
Log P means, so you can ignore this part. So let's go to the, okay, good question. So let me show you. Oops, geez. Oh, what happened to my screen? So P chi-square. All right, let me stop here and show you this. Can you see my screen?
Yep.
Okay, so here, so if you look at this information page, you're going to see a lot of detailed information about this function.
Okay.
All right.
Okay,
So here, so the vector of the quantiles here, so that's no problem. Let's look at here. So df means the degree of freedom. So here you need to specify the degree of freedom. In our case, that's 1, right? And the non-CP means the non-centrality parameter. That's easy. Okay, let's look at here. So the log
Okay.
P means logic, whether yes or no. So that's the probability P are given as log P or not. So
Mm.
here, so we just put, so usually I don't worry about this. I just put the default there, or I even do not specify this because I use the default. So the log P is not. So we use the original P, not the log P. Okay.
Okay.
And the only part I want to specify is here. So here, the log tail, whether the log tail is true or not, the default is the lower tail. The default setting is if you do not tell the R anything about whether the lower or upper tail, so it will take by default the lower tail is true to calculate from the lower tail to the cutoff. Okay.
Mm.
Okay. So you remember this. Okay. Let's go back to the, because I have to. Sorry, I have to switch the windows to show this. Okay. All right. So by default, it's the lower tail. What is the lower tail? Lower tail means like, so for example, if you want to see the 3.84, right? So in statistics, we use the small f to represent the density function, which is this, right? I just showed you. This is the density for this x, but we use a big F here to calculate the CDF. What is the CDF? This cumulative distribution function, which is the probability that x less than or equal to the value you specified, which means the area and the curve up to your point. So that's the lower tail, right? Okay. So if you, in the car, in the R, if you do not specify whether the lower tail or upper tail, the R will calculate the lower tail by default. So this will gives you what, then 0.95, right? The area under the curve, this area is 0.95. But if in case if you want to calculate the upper tail, how can we do that? We just use 1 minus this, or we just specify the lower tail is force. So it will calculate the upper tail for you.
So if you specify if the lower tail equals to false, then it will calculate the upper.
Yes, the upper, yes.
Higher area under the curve.
Yeah, so yeah.
Okay. Good to know. Thank you.
Does that make sense?
Yes.
Okay, so yeah, so here, so I try to make it clear because we have two functions here. So the small function, small f function means the density, which is a point value, right? But if you calculate the cumulative distribution function, which is a big F, so that's the area under the curve, either on the left or on the right. So this depends, so whether up or whether lower or upper tail, so totally depend on what area you want to calculate, right? Is that clear? Any questions about this? Very good, very good. So yeah, so when you have time, please try the article I provided, and to see if you can use the article, some of those, to help you with the calculations here, right? Okay. Now let's continue. Okay, so last time we very briefly introduced the mixture model. Okay, so this is a typical mixture model problem. So suppose this is a F2 population, and this locus A has like 3 possible genotypes here, and if this locus is exactly following the Mendelian segregation. So you're going to see three distributions, three underlying distributions, right? So for example, this is for the A2A2, and this is A1A1, and this is for A1A2. But if you do not see the genotype information, you can still, so if you just plot the distribution of the phenotypes, you can still like see an overall distribution, which consists of three underlying distributions, right? Okay, so this is a famous example, Fisher's example, the iris flower data. So by looking at the petal width or the petal length, so you can clearly divide the whole population into three subpopulations here. So this reminds me of Ryan's project. So Ryan is now working on a citrus project. So yeah, so the same thing. So this is the distribution you see, right? So when you look at the distribution of the leaf length and leaf width, so you see this, all right? So and I learned from you that the population you sampled actually are composed of three subpopulations here. So this is exactly like this. So this means like the first two subpopulations probably overlap each other very well. So if you put them together, they will show this peak, right? And there's a third distribution which is far removed from the first two. So that's why if you put all three together, so it will show this. So you can do experiment. So when you have the data for both the leaf width and the leaf length, you make the same plot, the scatter plot. You will see the things very similar to this one. So you can try that to see if you can, plot your data using this scatter plot, to see if the distribution looks like this. All right. Yeah, very interesting project. Okay. All right. So mixture model. So for each, so when we use the mixture model, so for example, if we look at a single individual, so if this individual comes from the case population, so this will be the model, right? The J's individual, if it comes from case population, so we can use this formula to represent the phenotype for the J's individual. Suppose J equals to 1 to the n is the sample size, and the K equals to 1 or 2 or 3, because here we are talking about a F2 population, and we know there are 3 subpopulations here, so that's why K equals to 1, 2, or 3, right? So if we want to model the phenotypic value for a specific individual from your sample, the J's individual, so if this one comes from the first subgroup, so we can use Yj equals to mu1 plus random error. Is that clear? Okay. Okay, so now this is the normal probability density function. We use this, the little f here. So now you understand what I'm talking about, right? The density function, the normal density function. So suppose this is a normal, and this is the normal density function to represent, so the value, the y value, when we have a specific value here. So what is the y value here? So that's the density function. Is that clear? Okay. Now, so we let k equals to 1, 2, 1 or 2 or 3, so indicate the 3 ordered genotypes. So we have 3 genotypes here, and we have many individuals progeny here. And so because this is a F2 population, and we assume if this locus is exactly following the Mendelian segregation pattern, then we have this information. So the proportion for the first genotype equals the proportion for the third genotype equals to 1/4, right? And the proportion for the second genotype equals to 1/2. Is that correct? No? Okay, so any questions here? We are talking about the proportion, mixing proportion. So because we know, so let's go back to here. So we have the whole distribution here, right? For F2 population. So do we know the mixing proportion for each genotypes here? For this one, and for this one? Yes, we knew, because this is F2. And then we knew this locus is following the Mendelian segregation pattern. So this should represent 1/4 of your whole population, right? This should be representing another 1/4. And the genotype in the middle should represent 1/2, right? So we use pi 3, pi 1, and pi 2 here to represent the mixing proportion. Because we mix them together, we are mixing these 3 subpopulations together. So we do not know each one is, which one is what, but we knew overall the mixing proportion for these 3 genotypes should be equal to 1/4 versus 1/2 versus 1/4, right? So that's the pi. Any questions here?
I have a question, Professor.
Yeah, sure. Hi, go ahead, Livy. Yeah.
Yes. So for the mixture curve, how do we know which curve corresponds to which genotype?
Oh, okay. So forget about the here. So this is just an example I took from the website. Let's go back to here.
Okay.
So your question is associated with this graph, right?
Right, yeah.
Okay. So we don't know. So we don't know which. So, but we knew so if this is a oops. So if this is a typical loci, let's say A1, let's say we have 3 genotypes for F2 population, right? Yeah, if this loci is associated with the phenotype, so we can use this. This is what we have learned, right? The mu midpoint plus A
Plus D.
plus D Z W and plus error, right? We can use this model. And if this is true, and this loci is following this model, so we can use this, right? Let's see. Okay.
Least square method.
So yeah, so basically we still can understand. So this one should be A1. This one should be A2, and this one should be A1, A2. Right?
Okay, got it.
Yeah, very good question. So any other questions here?
No.
Okay, good. Okay, so this is a mixing proportion. Now we have 3 mixing proportions here, and we can express the density for each individual using this mixture model. So if you look at the mixture model, so the single density function is actually the sum of 3 sub density functions here, right? Okay, so look at here. So for each individual, we can use the sum of 3 sub-density functions here to represent a single density function. So look at here. So k equals to 1 or 2 or 3. So we need to add up this equal to pi 1 plus times if it is the first category. So if this individual belongs to the first genotype, so then this is the first component, right? And we're gonna add up if this individual, because we do not know which subpopulation this individual belongs to. So we need to consider all 3 possibilities, right? So this is why we add up these 3 things here. So if this one belongs to the second one, then the second term will take it into account. And if the individual belongs to the third population, subpopulation, then we're gonna calculate this. So why is like this? So suppose, okay, let's look at here. Suppose the first individual belongs to the first distribution, first genotype here, all right? So then, so this phenotype will fit this density distribution very well. Do you agree? If this individual comes from the first subpopulation, then this value, this phenotypic value will fit this density function very well, which will make this value very large. Okay? If this individual comes from the first subpopulation, so we have like three populations here, right? So if this individual actually comes from the first one, so when you calculate the density function, this will give you a very big value here, right? Can you follow me? Any questions? It's not that clear. Let me repeat this. So this is very important. That's why I want to emphasize this. Okay, so let's look at the 3 distribution here. This is the mixture, right? So actually, the first one is following this distribution, and the second one is following this distribution, right? And the third one is following this. Actually, this is the first one. This is the second one, and this is the third one. Okay, suppose this individual came from the first one. Let's look at here. So it should likely located in somewhere here, right? Do you agree? The phenotype should be here. So when you want to calculate density function for this one, so this will give you the density function for the function 1, which is here. But if you look at here, for the function 2, it will give you a value here, right? Can you see it? And if you use this value to calculate the density function for the distribution 3, it will give you a very small number here. Can you follow me?
Yes.
Okay. So this is why. So if we use this to calculate I1, F1, Y plus pi 2, F2, Y, and plus pi 3, F3, Y. Yeah, if this Y actually belongs to the first first distribution. So when you try to calculate the density function with the first distribution, this will give you a very large number here. This is very large. But if you do the same thing using the same number to calculate the density function for the distribution 2 and 3, so these two values will be very small, like this. Can you follow me? So if you add up these three things together, so actually the sum mainly represent the first distribution, which is correct, right?
So the sum of all three is equivalent to the first distribution.
Yeah, so not equal to the first distribution because we also consider the mixing proportion here, right? But you can see if you add up these three things together, the sum mainly represent the first distribution, because the density you calculated for the second distribution and the third distribution is trivial, so it can be ignored, right? Look at here.
How do you deem them trivial?
Trivial. So let me.
How do you determine them to be less significant than the first?
Let me. Oops.
You need to hit the back button on the left-hand side.
Oh, you cannot see it?
No, you got it.
Oh, you can see it? Okay, good. So let me insert another blank page so I can have more space to show you. Okay. So yeah, this is a hard concept, but look at here. So this is the third distribution, okay? And this is the second distribution, density function. And this is the third one. No, this is the first one, actually, A1.
So it's the value because of its value on the x-axis? Is that why?
Y-axis.
Oh, its value on the y-axis. That wouldn't.
Yes. So let me show you. The x-axis represented the phenotype you want to look at. So this is the y-axis, and this is the x-axis. So here is y. So the phenotype, and this is the Fy, the density of Fy. So suppose now we want to calculate the density of Y, a specific individual, right? If this individual comes from this population, so the Y should be around here. Do you agree?
Yeah, it should be around the point of
Yeah,
A1.
because this one has the larger phenotype, right? So if this individual comes from the first subpopulation, the value of this individual should be somewhere here. Do you agree?
Sure.
Yeah, if there's let's say this is Y11, if there's another individual which is Y12, so if this one belongs to this second group, so you should see the phenotypic value for this individual should be around here because yeah, the distribution is here, right? And if you have a Y22 from the third subpopulation, so you should have a phenotypic value which is very small. Do you agree?
Mm-hmm.
Okay, now just look at this one, the Y11. So if you use this value to calculate the density function for number 1, so what is the density function value? It's here, right? It's here. Okay, but if you use the same value to calculate the F2 using Y11, what is the value? It's here. So this is the F2, right? But if you use the same value, so this value will be associated with here. Do you agree?
Yep.
Okay, now if you extend this, the third distribution here, it's even worse, right? So the density function goes here. So if you still use this value to calculate the density function based on the third population, so this value will be even smaller, right?
Mhm.
Okay, now we want to add up these three things together, but we're gonna multiply this by the pi1 and pi2 and pi3. So
Which is proportionate which in contribution to these curves.
I say that again, I'm sorry.
Pi is the indicator of the proportion that contributes.
Yes, that's right. That's
Okay, I
right. Okay, so now very good. So this I like these slides. So okay, so let's keep this slides. Let me. Okay, so suppose we want to calculate the F11. I hope I can have like more space. So this is the first component should be large, right? And the second component should be small, and the third one is smaller. So this sum, if you add up these two, the whole thing will mainly represent the first distribution, right? Okay, now if you calculate the density for the 1, 2, this will change like this. The first one is small, but the second one is big, and the third one is small. So if you add up these things together, so this will gives you a thing which is which mainly represent the second group, right? But if you calculate F22 here, and this will gives you the first one is small, the second one is small, but the third one is large. So if you add up these three, so this will gives you a sum which mainly represent the third population. Does that make sense? Very good, very good. Okay, any other questions? So before I erase this, no? Good. Okay. So this is very hard part. So I hope like we can all of us can follow this, and so this is important. So now we understand this part, right? Any questions? Any problems with this part? So this is how we use the mixture distribution to represent the mixture model. And now, since we have this formula, we can calculate what is this. Can anyone tell me what is this function represent?
So a sum of all of the a sum of all of the proportional phenotypic values.
Mm-hmm. So for each individual, we calculate a mixture, right? A mixture of this, and we add up all the density functions for all the individuals. Suppose in this F2 population, we have M observations, M progeny. So we add up this all these individuals together to form a log likelihood. Do you still remember log likelihood?
A little bit.
A little bit. So can you still remember? So what? So why do we need to calculate the log likelihood? So why do we need to do that?
To maximize the observation data?
Yes, because we have an underlying distribution, right? So we have the underlying distribution, but we do not know the parameters here, do we? Do we know the parameter? No, because we only see the phenotypes, but we want to estimate either the average genotypic value for each subpopulation, or we want to estimate the additive or the dominant effect at this locus, right? So we do not know the parameter. So we can assume the underlying model with these unknown parameters, and we can use this to calculate the joint probability and then the log likelihood. And then we can do the first derivative and then the second derivative and set those equal to 0 to find the maximum likelihood estimation for those unknown parameters. Can we? Yeah, this is the logic behind. Is that clear? But the situation here is a little bit different because this is a missing problem, right? Because we do not know the genotype data for this locus among this F2 progeny, right? So that's why we use the mixing model here. Any questions? Yeah, I would like to stay slower to make sure everybody understand this. All right, no problem. Let's continue. Okay. Oops. So this is another confusing part. So, all right. So we define the two new random variables here. Okay. The first one, the eta. So we use eta to for each individual. Let's say we have 1 to n individual, and for the jth individual here, so we use this random variable eta j to model the genotypes. Okay, so if this individual, the jth individual, comes from the first population, we let the eta j equals to 1. If this individual comes from the second population, eta j equals 2, and so on, right? Okay. Now, based on this eta j, we then define a new function, random variable delta. So this delta is different from the NCP. What is NCP? The non-centrality parameter in chi-square distribution. So we use the same notation, but with different meanings. So don't be confused about that. Okay.
What is it being used for n? I'm sorry, Professor.
Uh-huh.
I'm sorry for interrupting. What is that n? Is that a different form of n, like a Greek letter?
Oh, you mean this n?
Yes, because the typescript that's used seems a little bit different. That looks.
Oh, you mean here, right? This is not okay. Sorry. Yeah. This is not n actually. So I know this is the most confusing part. So let's make it clear. So first we have this many individuals. This is little n. So this is n, but this is not n, right? This is let's say eta. So this is a Roman Roman letter eta. So
Okay,
this set is a little bit longer. Okay. So we use n to represent the total data points. So for example, for this experiment, you collected n progeny from the F2 population. So that's the n, okay? But here it's not n, this is the eta j. So for each, for example, for j's individual, out of this n progeny, so we knew this individual must come from one of the three populations, right? Subpopulations, but we don't know which one it comes from. So we define this eta j as a random variable, which will be equal to 1 if this individual comes from the first subpopulation, first genotype, or 2 if this one comes from the second genotype, and so on. Is that clear? So based on this eta, so we can define another indicator function here. So this is function. So in this function, we will compare whether the eta j equals to this k. So if eta j equals to k, then the whole thing, so the delta, the whole thing, the whole thing will be equal to 1. Otherwise, this indicator function will be equal to 0. So am I clear? This is very confusing.
Can we go over it one more time, Professor?
Oh, yes, sure.
Thank you.
No problem. Okay. So now this part is clear, right? So we have 1 through n.
Progeny.
This is little n. But for, let's say, for the j's individual, we just pick out a specific single progeny, the j's one, and we want to use this eta j to indicate this individual's genotype. So there are 3 possible genotypes, right? One, if eta j equals to 1 means this individual carries this genotypes at this locus. And 2, and 3. Okay, now given this, we can define another indicator variable, which is eta. So in this indicator function, so we will compare this variable with any cluster. So k equals to 1 or 3 or 2 or 3, right? Okay, so if this one equals to 1, then theta 1, 1 equals to 1, but theta 1, 2 equals to 0, and theta 1, 3 equals to 0, 2. Is that clear?
Yep.
Okay. Oh, right. Very good. So, oops. All right. Okay, now look at here. Suppose this one comes from the first subgroup, which is like genotype equals to A1. Then, so this is the, see, this is the mixture model. We put the 3 subpopulations here, right? So if this one comes from the first subpopulation, this will becomes 1, right?
Right.
But how about here?
0, 0.
And 0, right? Then this whole thing is gone. Whole thing is gone. Only leaving this part, right?
Yes.
So that means like, okay, so this phenotype should be roughly equal to the average of the first population. That makes sense, right?
Right. Okay.
Okay, so let's look at another, let's say Y W, another individual. So if this one comes from the 3rd population, so in this case, this one will become 0, right? This one, how about this one?
0.
0, how about this one?
1.
Yes, so then this is gone, and only leaving this part. That makes sense, right?
Yes.
Okay, so this is how we define this model using 2 newly defined random variables. Because so it looks complicated, but it is very convenient to use them for the presentation and for the matrix calculation. That's why we use this way.
Okay, got it.
Any other questions? Any problems for other students?
Yes.
Okay.
So-
Yes. Right.
Change the, so at one instance you said okay 1 0 0, and then you changed it for some reason. What change did you make to change the combination of what is a value of 1 and what is a value of 0? What did you change?
Okay. So, oops. Let's. Yes. Okay. Oops. Okay. So here, actually, we call this kind of function as an indicator function. Indicator. So that's why the value of this indicator function, the theta, will take either 1 or 0. And this 1 or 0 actually indicate which subpopulation this individual comes from. So for example, if this one comes from here, then look at this mixture model. So this one will be effective because the whole thing here is 1, right? And we're gonna include the average of the first population into the model. But here, this becomes 0. So we're gonna eliminate these 2 terms here. So indicator means this. Does that make sense to you?
Okay, I see. So it comes from a specific population. That value is considered 1. And so NJ1 will have a value of 1, but then NJ2 and 3 will have a value of 0.
Yes, yes. So totally depend on where, in which subpopulation this individual comes from, right? So,
Yep.
Okay. All right. So because this is the perfect situation because we assume we knew this, but in the future we're going to change this information because we do not know this indicator. We're going to infer this indicator variable using our data. Does that make sense? But for now, we just assume we knew this and we put this in the complete model. but in the near future, I'm going to show you. So unfortunately, sometimes we do not know this indicator, so we have to use our data to infer this indicator random variables, right?
Sorry, Professor. Yj here is a probability function, right?
Yj is a probability function. So could you say that again?
Y index j
In
on the
y,
third line,
let
after the
me
indicator, after
so let me erase this first, and then so
the
your question is why this yj, right?
yeah, what it is it the probability density function?
You mean here?
As f of x.
F. Oh, you mean here, right?
Yeah.
This a density function?
This whole formula is calculating the probability for the mixed probability.
Okay, so yeah, this is a good question. So we are not there yet. So here, this is not the probability density function. So first, we need to use this indicator to model where, from which distribution this individual comes from. And then next step, we're going to include the density functions, probability density functions, to help us to fit this model into the mixture distribution function. Is that clear? No? Okay,
Yeah.
let me repeat. Okay, sorry. All right. So here, maybe next slides. Okay. So, oops. So this step, we are just get ourselves ready for the probability density function, but now we do not use the density function for this step. So here we just want to see, use a model to represent how we can link the phenotypes for this individual with the population mean 1 or population mean 2 or population mean 3. And then we can link this yj. So this is the probability density function, right? To the summation of the this is k, yj, and pi k, k equals to 1, 2, 3. So that's the link between this and this. So this is the original model. Once this is defined, we can use the probability density function to get the mixture density. Is that clear?
Yes, thank you.
Okay, sure. All right. So any other questions here?
I have a question.
Mhm.
So why are we doing this? So what are we going to calculate? It's the mu1, mu2, and mu3, right?
Yes, this is the parameter
We want to estimate. Okay.
So why we do this? Because we want to use this model to form a linear regression model. Then we can construct the log likelihood, and then we can easily get the solution for this estimations.
Mhm.
Okay. All right. So now we have defined this and this and this, right? So we just put them together as a vector. Okay. So for each individual, there will be a vector of length of 3. So for each individual, we will have like something 1, 0, 0. For another individual, we're going to have 0, 0, 1. Another individual, probably we will have 1, 0, 1, right? Something like this. All right. And then, so this is the variable we're going to use. Remember, here we assume we knew these numbers, so, but later on we're going to see. So if we do not know this information, how can we how can we still analyze this data to get the MLE? Okay. All right, so this beta is the parameter. So represented the 3 population means, right? We want to estimate. So this is equivalent to the previous one. So in the past, we learned beta 1, beta 2, and beta 3. So these are the same. So we just use the mu1, mu2, and mu3 to represent the population mean for these 3 genotypes. Is that clear? Okay. Now, once we have all this set up, so we can have the MLE. If we knew this theta, how do you pronounce this? Theta?
Beta hat. Beta hat.
Data hat. Okay, thank you, Ryan. All right. So suppose this data are known, so we can easily get the MLE for this beta, right? So this is what we can do, right? And also we can get the estimation for the variance of the residual error using this. Any questions? If missing variable were not missing, so then we can easily get the MLE based on that linear regression model, right? Okay.
Right.
All right. Now the problem is like, yeah, unfortunately, we do not know those. Say that again, right? What is the number? So how do we pronounce?
That is delta. That is
delta. That is the delta. Okay, delta. Thank you. It is so hard. Okay, suppose we knew these missing values, then we can easily get the MLE. However, if we do not, then we can use the very famous EM algorithm to help us to solve the problem. So, okay, because we do not have these numbers, right? The delta, so we can calculate the expectation for these things. And once we have the expectation of these things, so then we can treat this. So at each step, iterative step, if we can calculate the expectation of these things, of this delta or delta square or something like this, so next step, we can treat this as a complete data problem and use the M step to find the MLE for the parameters. So we can just alternate these 2 steps, E step and M step, and E step again, and M step again, and so on, until we get a convergence. Okay, so, and then when the program converges, so we get the solution, and that's your estimation of your mu1, mu2, and the mu3. Okay, is that clear?
I have a question about the E step.
Mm-hmm.
So in E step, we want to calculate the expectation. So what's the parameter we fixed when we calculate the expectation number?
What
parameter we are fixing when we're doing the expectation step?
Oh, I'm gonna show you, shortly. Yeah, so here, okay. So first, so only this thing is the theta. The theta is missing, right? And so in the expectation step, we only need to calculate this expectation of this, and then, all right. So in the initial step, so we have to let the program. So we have to set up like initial value to the program. So, and this is the fixed value we can use at the starting point. And then based on this, we can estimate the beta and the sigma square. Is that correct? Is this the question you ask?
but what is the theta? Like in the density function, what is the theta?
Or
It's
what is the, you mean what is the theta here?
Yeah.
All right, theta actually equals to, there are 4. Theta equals to mu1, mu2, mu3, and sigma square. All right, so this is the things we want to estimate, right? So one, at the initial time, you just randomly give them some values here. And in the first step, and based on this, you can easily calculate the expectation of this. And once you get the expectation of this and treat this as the realized value, and then you can go back to calculate MLE for these parameters to update this value. And once you update this value, you can go back again to calculate another round of the expectation of this. So once you update this, you can go back again to calculate the MLE for these parameters and update this parameters again. And so this is the iterative, right? Iteration. And each time you're going to check if the estimated, the currently estimated parameter is close enough to the previously in the previous step. If they are very close, which means the convergence has been convergence has been achieved, then you're going to stop your algorithm. And at this point, you will get the best solution, MLE, for your parameters. Does that make sense? Not really?
I'm getting it.
Oh, say it again. I'm sorry, Ryan. No
I'm
problem, right? Oh, okay, great. Very good. So, oops.
how can we so so the expectation value, the function to calculate the expectation value. So how can we know it's this formula?
You mean this formula? This one?
Yeah, the packet, yeah.
Okay, so this is by definition. Let's see. So what is the so let's see the meaning of this expectation. So what is the here? So here we're talking about a specific individual, right? So we want to calculate whether, so what is this? So this is the expectation of, let's say, whether this one equals to, let's say, equals to 1, k equals to 1. What is this, right? So what is this? So if you look at here, so this is the all possibilities, right? If you add up these 3, so this is the all possibilities that this individual will will belongs to the first,
The second,
and the third. And the numerator is just focused on this. So this is how we define the expected value for this individual belongs to the case group, right? Does that make sense? Yeah. So let me show you this. So what is the expectation? Let's say Y belongs to the first group. Can we use this? So the probability that Y belongs to the first group plus the probability Y belongs to the second group, and plus the probability Y belongs to the third group. That's the denominator, right? And in the numerator, we just put probability that Y belongs to the first group. That's the expectation of Y belongs to the first group. Do you agree? Yeah, so the same thing here.
But so like we don't know that the individual belongs to which group.
Right. So
But
that's
so for each individual, there will be 3 values for each one for one individual.
Okay. Now let's yeah, this is a very interesting question. So yeah, I think yeah, I understand where the confusion came from. So here, so suppose, so let's see. So suppose this is the E step, right? We want to calculate this. So what do we know at this step? So what do we know? Do we know the theta? So we knew, right? Because we knew
Yeah.
the theta. Beta 1, let's say beta 1, beta 2, and the beta 3, right?
Mhm.
And the sigma square, right? We knew this. So this step has been updated in the previous M step, right?
Mhm.
Okay. Now, based on this, can we calculate? Can we know the density function for 1 and 2 and 3 for any value? Yes, of course, right? Because the parameters are already known, so we can know exactly the density function for 3 populations, right?
Mhm.
That's here. And we also know the proportion, the mixing proportion, because this is F2, right?
Mhm.
That's the F2 population. Then everything is known. Then we can, and what do we know here? So we knew that this individual's phenotypic value. Do we? That's the data. We knew that, right? So we can easily calculate this. Can we?
Mhm.
Yeah. So and okay. So now here. So suppose for the first distribution, we knew the density is this much, okay,
Mhm.
for this individual. But for the second density function, we knew
Small.
they're small, and third one is small.
Or-
So then how can we use this information to calculate the expectation, whether this individual belongs to the first category? These are just like the probability that this individual belongs to 1, right?
Mhm. Okay.
This is belongs to 2, right? This is belongs to 3, right?
Mhm.
So if we form this ratio, then we can calculate the expectation that why this individual belongs to the first population.
Mhm. Okay.
Okay. Yeah, it's very hard. I know, yeah. Any questions here? Okay, so this is the E step, the expectation step. We use this information given the updated parameters in the previous M step, we can calculate this, and this will be the expected value for the missing value. And once we have the expectation of this missing value, we can treat this value as not missing. Then we have a complete data problem, right? Then for the next M step, we can easily use the beautiful, nice form to calculate the MLE for the parameters, and we can further update the parameters value. And then we can iteratively do this EM algorithm until the whole process converges at some point. Once this convergence criteria is met, so for example, the difference between the T step and the T plus 1 step, the difference between the estimated parameters value between the T step and the T plus 1 step is sufficiently small, then we can stop. And this estimation will become your MLE estimation. And then you are done with your job. So you can successfully estimate the population means for these 3 genotypes. So is that clear?
So convergence is the final step once we have reached the convergence criterion. But could you describe it a little bit more? I'm not quite grasping what convergence is.
Oh, okay, sure. let me draw another graph. So hopefully that will help us to understand this. Okay. So first, at the first step, we will initialize these parameters. So we want to estimate this, right? So we just randomly give them some values here. So mu1, mu2. This value may be very close to the real value, but maybe not. But anyhow, we don't worry. We just give them some initial values. So this is the start point of this EM algorithm. So once this is given, so we can calculate the expectation, right? And okay, so now with this expectation, so we can go back to re-estimate these parameters. So let's say time 1. This is time 0. Time 0, we just give them some arbitrary values to initialize this process. But once we use this initial value to calculate the expectation, we can go back to re-estimate these parameters. We get another mu1 star. Let's say mu1. Let's say this is mu1 0, mu2 0, mu3 0, sigma squared 0. And at the step 1, we can get mu1 1, mu2 1, mu3 1, and sigma square 1. So this is for the first step, right? Okay. Now we can check if these values are close to these values. So then we can take the look at the difference between these values, right? Of course, at the beginning of the process, they are quite different because they are not converging, right? So the second step estimation might be quite different from the initial step. Do you agree? Because your initial guess might be wrong. So that's why you see a big difference. However, if you continue to do this, because once you finish the first step, you can use the updated parameter value to recalculate the expected value for this. Can we? Yeah, once you updated this expected value, you can go back to re-estimate the theta again. Now we set the step 2. So you have another updated mu1, but step 2, mu2, step 2, and mu3, step 2, sigma square 2. Is that clear? But at this step, you can compare the step 2 parameters with the step 1 parameters to see if they are close to each other. You just look at the difference between these numbers, right?
Mm-hmm.
So imagine, so maybe this time the difference becomes smaller because you are getting closer to the real value.
Oh, the difference is the convergence.
Yeah, the difference is convergence. So if you look at it here, so we just compare the difference between the theta value. Theta represented the parameters you want to estimate, right? So we want to see how close the values you estimated for these parameters at time t1, t plus 1. So we want to evaluate at each step, we want to evaluate how close or the difference between the values for the parameters you estimated at current time versus the values you estimated at the previous step. So if they are sufficiently small, which means, yeah, the next step, if you do the same thing, you get almost the same identical estimation for this theta. So do you think you need to continue this process, or you're gonna stop? You're gonna stop because you're gonna repeatedly get the same values for the theta, right? Is that right?
Yep.
Then you're gonna stop. So that's the convergence criteria. Oops. So if you draw a plot like this, so the first step, you give the value here, but second step is here. But next step probably becomes here. So there's a regression. The difference becomes smaller and smaller. And finally, even you continue the process, still you get the identical solutions, right? And then, so you're gonna find a place that you're gonna stop it. And this estimation will give you the best estimation here. Does that make sense?
Yes.
Very good. So this EM algorithm is a very popular one. So because in reality, in your future data analysis, I believe the missing data problem is always there. So how can we solve those problems? So this is one way, a very good way, a very nice way that we can consider using to solve your problem. So because if you do not have missing data, you have all data available, then you can easily get a nice form solution for your MLE, because that's a complete data problem, right? But in reality, you may missing something, so then you can treat that as a expectation. So you use the expectation step to solve that problem, and then you just treat this new data as a complete data, and you can get a very nice form for the MLE, and then you continue this iteration until it converges. Then, bingo, you get your solution. So yeah, it's tough, but it's fun to learn this because it's very useful and it's interesting. Do you agree? All right. So I think I'm gonna stop here because today we have learned very tough stuff, and I hope to give you some time to digest. And so I believe some of you probably have some questions for me. So you can send me email to ask, or we can talk about this, continue talking about this in the afternoon during the office hour. So before we dismiss this class, so do you have any questions? So I can explain for now.
Yes.
Mhm.
Why I'm looking ahead at the slides. Why are we going through the entire, not only the derivation, but also the proof of this algorithm?
Okay, so first, that proof is not required for you, just for your information, because it's very complicated. So the proof is to show, okay, so first, if this is a complete data problem, so we can easily get the MLE, right? So that's the best answer. But because we do not have the complete data, so we have to use the EM algorithm. But the EM algorithm, in each M step of the EM algorithm, we still use the MLE. So we want to prove the final solution from EM algorithm is equivalent to the MLE from the complete data problem. So this is why we want to show they are the same.
Okay. So we're going to go through those relatively quickly.
Yes.
Moving on to.
I don't want to scare you away. So that's too complicated. So I don't require. Yeah. That's only for your information. So because some of you may have the question in your mind. So yeah, EM algorithm looks beautiful, good, but by doing EM algorithm, can we get the unbiased, the right solution? So this is the proof. So even we use the EM algorithm involving the missing data, we can still get as good a solution as the complete data by using the MLE. The same. Yeah. Do you like it? It's tough, but it's very useful. So I believe many of you will enjoy the beauty and the powerful EM algorithm in your future research career. Any other questions? Okay. So, so any questions I can help for now? Yeah, I hope you still enjoy. Yeah, today's class is relatively tougher because it needs some like reasoning so behind, because we have so many like newly defined parameters. So first you need to make sure you understand why we do that, and so their definition and their meaning, and then why we put them together to form a linear regression model, and then so how we treat the missing problems, how we deal with the missing parameter, missing data, and then how we use the EM algorithm to help us to solve the problem. Okay. All right. Sounds good. Okay. All right. So I'm gonna be available in the afternoon if in case you have questions, so we can talk about that. Talk about your questions at that time. Okay. Okay. Now, bye bye for now. Thank you.